आपको दिखाई नहीं रहा इसमें?
ठीक है, जाने
दो। ठीक है, दिख रहा है ना स्क्रीन?
Then I'm not connecting. Huh?
स्क्रीन में विजिबल है।
बकवास है यार। Who's I'm put this. I'm not sure. एक second.
अरे यार
Okay.
ये फुल स्क्रीन नहीं होता। तो कर लो इससे। एक बैठो तो फुल स्क्रीन का साइज। कैमरा में तो ये करेगा। ये वाला तो आगे पीछे के लिए नहीं ठीक है।
Hello. Okay. Can't we sit here? Okay. Okay, put on. Should we start?
Yes.
Hello everyone. We are presenting a paper on partition core approach to tokenization. This paper presents the tokenization as optimization problem. In this paper, our objective is to minimize the number of tokens per word. Introducing notations. Sigma is a set of alphabet and C is a corpus. It gives a function of mapping from each word to its frequency, and partition is a function which gives a number of minimum number of tokens that can be chosen from us concatenated to get the word. And formulating the search problem. In this, we optimize the function summation of partition into count for each word. This gives the total number of tokens used to represent the entire corpus. This is to be minimized. To comment on hardness of this problem, we convert this into decision version. In decision version, we use an additional variable L and try if we get a such set. This optimized objective function has a value less than L. Proving NP hardness, we reduce the vertex core problem into this, which is already known to be NP hard. Vertex core problem is choosing a subset of vertices which cover at least one of vertexes each edge. Decision variant of vertex core problem is decision variant is for given integer k, is it possible to choose a vertex cover of size k? For this, we use a construction from an instance of vertex core problem to a toke problem. It can be seen that we can construct an S instance of toke problem from a given S instance of vertex core, and also similarly we can construct the reverse. From this, we can conclude that as we know vertex core is NP hard, our toke problem is also NP hard. To design approximate algorithms for our toke problem, we face challenges mainly due to two. In general, we use two approaches to design approximate algorithms. One is to prove whether the objective function is either submodular or supermodular, and the second is relax and round approach, where we relax some constraints and bound back the result to nearest integers. Both are not possible here as our objective function is neither submodular nor supermodular. And the second is not possible as real world NLP problems has large number of variables and constraints, making it computationally infeasible. Formulating our problem as mixed integer problem. Here we define an additional function cover, which is maximum number of concatenations of adjacent singletons in W, forming the tokens in S without reuse. It can be seen that the partition plus cover for any word is length of word. This can be intuitively proved by the illustration that for every token, a 1 is counted in partition as number of tokens, and the length of token minus 1 is counted in cover as number of adjacent concatenations. So summing up partition and cover for any word will give the length of word. Reformulating our problem with this relation, we can reformulate it as maximizing sum of count into cover for over entire corpus. Formalizing our problem statement by introducing some variables. Xt is variable whether a given token t is chosen in the final status. Mi plus 1 w is represents whether I and I plus 1 letters of w are covered by same token. Mi plus 1 wt is whether it is covered by t or not. We can introduce some constraints. The first constraint ensures that the size of subset S is at most k, and the second constraint ensures if it can be covered by a token t only if it is chosen in S, and if two adjacent singletons are covered using same t, using a t, then it must using same token, then it must be covered by sum of token in t, and every adjacent singletons are covered by at most one token. And the constraint 678 ensure that the continuous segment of token is the continuous singletons are covered by same token if it contains a continuous substring in the word. And 7 and 8 ensures whether ends are managed properly. By relaxing some constraints of our talk problem, we can reduce it to vertex maximum coverage problem. In this problem, given a set of elements and corresponding weights and a collection of subsets of L, we should select a subset of U such that the coverage is maximized. For this, we introduced Li as whether than a particular element is covered, mu j as belongingness of particular subset in the final subset U dash. Similar constraints to our talk problem can be enforced here. And the constraint 10 ensures a subset size limited to 10, and 11 ensures whether if an element is covered, it must belong to one of subset of U dash. The constraint 10 is parallel to constraint 2 of our talk problem, and constraint 11 is parallel to combined constraint 3 and 4 of our talk problem. It can be seen that here sum of constraints of our talk problem has no parallel constraint. So we can see this as relaxation of talk problem. So we can design an greedy WMC approach for talk. This is by we have an instance of talk problem, and we'll convert it into corresponding WMC problem by variable parallels described in the slides above. And for this corresponding WMC instance, we apply the greedy WMC algorithm, which is proven to be 1 minus 1 by approximation guarantee, and we'll transform the solution of greedy WMC back into the talk. But here the trick is the subspace of WMC is superset of TOC as we have relaxed some constraints. So the corresponding TOC solution obtained may not be feasible, but we can comment that maximum value obtained using this using graded WMC may exceed the true optimal of TOC. Now coming to
grid of algorithm. Grid of algorithm mainly consists of two steps. One is selecting token set S. First step is selecting token set S. Second step is tokenizing words using S. Step 1 consists of first we construct a candidate token set T considering all substrings of length greater than or equal to 2, and f of S is the MIP objective value for a subset S. We start with the null set S and iteratively we choose token T from candidate token set T which has maximum marginal gain, and we continue this process until size of S is k, and here priority order is order of inclusion in set S. Coming to step 2. Step 2, in for a given word F, W, we identify the potential token covers by scanning the W, and we sort the potential token covers by their priority order. We apply tokens in their priority order so that MIP constraints are not violated. We flip the corresponding MW bits, ensuring that that substring is covered. Here is an overview of byte pair encoding algorithm. In BPE algorithm, we initialize the dictionary with each character as individual token, and we count most frequent adjacent character pair, and by merging those we create a new token. We update this new token in entire corpus. We continue this process until the size of vocabulary is k. Coming to the complexities, complexity of choosing token set S in grid token is order of mod t into k into sigma of length of the words. Here we have extra order of mod t because we have to scan all substrings of length greater than or equal to 2, and for each string we have to evaluate f of s. Coming to the BPE, we do not have to do this extra scanning over all substrings. Here we iteratively merge most frequent pairs. And coming to the complexity of tokenizing a word, in grid token algorithm, after for scanning potential token covers, it is order of W square, and extra log W factor is for sorting. In BP, there is no need to sort because there is a fixed order of merges, so it is order of W square. Grid token has higher complexity, but both methods are practical for NLP task. Although grid token complexity is more, it is better than BPE because there is flexibility in custom tokens. In grid token, we can directly add custom token into token set S, but whereas in BPE, we should incrementally add sub tokens in order to construct required token, which needs unnecessary sub tokens. And effect of tokenization order in BPE, if we cannot insert custom token before or after, because if we insert before, it may prevent later useful matches from happening similarly later, which can disrupt token formation. In grid token, there is no problem. We can freely add new tokens in S, so that we can conclude that grid token provides better control over token selection. We evaluated grid token on 4 data sets. They compared grid token against BPE on 3 metrics. First metric is both have same fixed count k, same token size k. In second, and they are compressed until both tokens are compressed until they have same compression. Third is difference in token selection. From the results, we can say that GreedTalk achieves 3 to 5% fewer tokens per word than BPE, and GreedTalk requires 13% fewer tokens than BPE to reach same compression utility. From the graphs above, there is divergence between GreedTalk and Talk, which says that GreedTalk chooses tokens with more compression utility, whereas due to pairwise merges, BPE prevents from choosing these tokens. Coming to the GreedTalk's approximability, we define GreedWMC val as the objective value obtained from GreedWM approach to talk, and GreedTalk val as the objective value obtained from above algorithm. We define performance ratio deinst as GreedTalk val by GreedWMC value. Here, GreedTalk guarantees that its objective value is at least deinst into 1 minus 1 by E, because GreedWMC has approximation to GreedWMC of 1 minus 1 by E. Optimal WMC value is greater than talk value because there is relaxation of some constraints. Here is graph of deinst against K for 4 data sets. Initially, it decreases because GreedWMC selects some overlapping tokens, whereas in GreedTalk restricts them. As K increases, these overlapping tokens are eventually replaced by single tokens. We can conclude that for sufficiently large K, deinst has at least 0.9 value. We can say that GreedTalk algorithm achieves at least 0.9 into 1 minus 1 by E of the optimal talk. For increasing tokenization efficiency, one way is to decrease the candidate set size T. We can do this by leveraging the domain knowledge. One approach for this is we divide the corpus set into domain-specific subsets and apply GreedTalk in each subset to get intermediate sets S1 to Sk. They form final set T by combining substance of length greater than or equal to 2 from all of these subsets, intermediate sets S1 to Sk. This approach is done on the CJK dataset, which shows reduction in candidate size set from 320 million to 231K. We can optimize our computational efficiency by adjusting the maximum word length W and candidate token set size T. This is done on Wikipedia articles dataset, which has 700K to 800K words per second. They achieve this. We can conclude that GreedTalk is both efficient and scalable for large-scale NLP tasks. For coming to the second paper, when every token counts, optimal segmentation for low research language models. Large language models often they have revolutionized NLP, but they have some challenges. Low resource languages often have low performance due to limited data availability, and BPE may fragment tokens inefficiently. And for longer token sequences, it takes more time and memory usage. Here we propose an optimal segmentation algorithm to improve token efficiency, especially for low resource languages. Tokenization process generally involves 3 stages: pre-tokenization, vocabulary construction, and segmentation. In pre-tokenization, given text is converted into consistent format. In vocabulary construction, we construct a dictionary from the given text by frequencies of words. In segmentation, we convert given text into tokens by using the constructed vocabulary above. Here we focus mainly on segmentation to reduce token count and to improve efficiency. Here we define metric token saving ratio as SB of D minus SC of D minus by SB of D, where SB of D is number of mod of this is number of tokens needed for segmenting document D using strategy B, and similarly for A. We use this metric because higher TSR implies that fewer tokens are used, and that implies lower computational cost. And this is important for lower resource languages for efficient model training.
Coming to optimal segmentation, the problem definition is that we have a vocabulary V and need to find a segmentation S star that minimizes the number of tokens for a document D. And the key idea used is that they used a dynamic programming approach and also a data structure trie for efficient token lookups. Here DP is an array where DPI stores the minimum number of tokens needed to segment the prefix D0 to DI. And they also used a parent array par which serves as a backtracking, which helps in backtracking mechanism where par I points to the end of the previous token in the optimal segmentation. And here this is the recurrence relation for DPI, which says that we need to find minimum of DP of j minus 1 plus 1 where j is from 0 to I, and the main step where dj to di also belongs to vocabulary V. And the main steps of the algorithm is to first initialize DP table to track minimal token count for prefix D0 to DI, and iterate over all possible token splits using a trie for lookup. And then we update DPI and par pointers for backtracking, and after getting, we reconstruct the optimal token sequence using backtracking method. And this is the algorithm for the above steps given in the paper. And the complexity for this algorithm is that the complexity of this algorithm is O of n into m, where n is the length of the document D and m is the length of longest token in the vocabulary V, which is same as for greedy BPE. And we get that space complexity also similar for both greedy BPE and optimal segmentation BPE, which is complexity is similar for both cases. And we experimented for these tokenizer configurations where we use default pre-tokenization and vocabulary and some different vocab sizes of OpenAI tokenizers. And there are two methods used for these evaluations, which are intrinsic and extrinsic, where intrinsic evaluations focuses purely on segmentation aspect of tokenization, which measures token savings using the TSR. And extrinsic evaluation investigates how TSR affects the NLP models by impacting on the perplexity and accuracy of the models. Intrinsic evaluation datasets are that they used CC100 dataset, which have languages and Wikipedia for English. The extrinsic evaluation task, the task selection is relied on intrinsic evaluations of languages. Here we selected English to show that there is no degradation in performances in language with near zero compression, and some low resource languages where we get the high TSR values. And we find that we include the metrics of perplexity and accuracy across these different models and task types. And we also check the performance on subset of datasets and compare the greedy and optimal tokenizations. Here we find that for all the cases, percentage of samples with non-zero TSR across datasets we get, and it focuses on, and the percentages are higher for the low resources languages, where we can see 100% for Turkish and etc.
And the baseline model configurations for extrinsic are they use fine tune on 2 different sizes of GPT models on open web text and evaluated the segmentation strategies. And the results of intrinsic evaluations are that this optimal segmentation preserves morphology, improving token efficiency. Whereas in greedy BPE segmentation, they often split words arbitrarily. For example, in the case of English, they split the policymakers as given and which does not preserve the semantic meaning of those words. And similarly, in other languages, it incorrectly splits tense markers and case endings and fails to preserve verb roots and also compounds. And the main quantitative findings are that it reduces token count by 3 to 5% compared to greedy BPE, and compression rates are up to 20% for morphologically complex words. And it benefits the most for agglutinative languages, as in greedy BPE there are excessive token splits for those languages. And we also find that longer words achieve higher token savings, which is based on this graph. For all the languages, it shows that word length appears to be the factor in compression efficiency across these all diverse languages. And for extrinsic evaluation tasks, we get up to 10% accuracy improvement in the NLP tasks. And the largest gains are for the low resource languages like Indonesian and Turkish datasets. And in English, we can say there is no degradation in the task performance because of the perplexity analysis. Here we find that perplexity is less for optimal segmentation in both the model sizes, and we can confirm that optimal segmentation does not degrade performances of English, even though English is not a low resource languages. And the conclusion is that we find an optimal segmentation algorithm where for the cases where there is inefficiencies in greedy BPE segmentation, our method, it results in better token utilization for mostly low resource languages. And we also found intrinsic evaluations gives the token correlation between TSR and linguistically meaningful sentences. And extrinsic evaluation shows performance gains in text classification and generation tasks, especially for morphologically complex words. And some of implications are that further improvements in low resource NLP applications are required, and suggest better segmentation strategies can enhance model effectiveness without increasing computation.
You go back to when you have started that intrinsic extrinsic one. So in this slide you have talked about what they are doing. Next slide. So can you explain how they are doing the extrinsic and intrinsic evaluation, how they are performing this evaluation, what exactly they are doing, and you have explained what. Can you answer how?
Like first we find TSR values based on intrinsic method.
How they are doing intrinsic?
In intrinsic, we just compare based on TSR values.
Can you go back? Now.
Here we compare using TSR value. In the in extrinsic, we use this tokenization and we measure perplexity and accuracy of that model using this tokenization. It is just showing that this compression algorithm is better than greedy algorithm. Here,
So you have written that you have used GPT and the authors have used GPT models for the application generation. So what exactly they are classifying for? What data set they have used to classify the thing?
Not mentioned.
What are the generation tasks they have taken?
give it task types.
Their question answering or in the design.
Like it is given in the below table on which tasks they have been testing, like generation task and classification task for English.
So these are the okay. So tasks mean how
It means what exactly is being
Like,
classified?
These are the models of
Using this tokenization method, they are doing generation task and they're measuring accuracy.
For example, English B2B. So what does it exactly mean? Is it a data set or
It is that model is doing a task.
అంటే task ఏంటని అడుగుతున్నారు బేసిక్
We don't know exactly what the task is, but they're measuring some task. They're measuring the accuracy on some task.
like in QQP we read that it classifies whether two questions are duplicates or not.
can you go to slide number 35? So here, from calculating case and mention there are two strategies. So, greedy and optimal. Can you explain what is greedy and what is optimal?
Like optimal is the one we defined in the below, and greedy is what used in general. Greedy.
Actually, this metric is defined for two strategies. Here we are using this for this tuple. Greedy segmentation is already segmentation which we are using. Greedy optimal segmentation is which we define here.
first paper, maybe slide 24. There is this mention of flexibility of adding section for the person. So what exactly flexibility will be?
In this grid talk algorithm, we are using set S for tokenizing the text. In that set S, we can directly add custom token in grid talk, but whereas in BP, we get tokens by iteratively merging frequent pairs. So for getting that token, we have to merge.
Like when we want to add a domain, like we have trained this vocabulary construction on for some corpus W, and we want to add some domain specific corpus to it. Then if we have some specific token in it, we can directly add those in this grid talk. But in BP, all for a specific token to be added, all its
Merges.
we have to get it by all merges.
So on the first paper, you mentioned something supermodular.
Yeah.
So how that is helpful?
Like submodular will when objective function is to be maximized, when it is submodular, then we can get diminishing returns on each equation. If objective function is to be minimized, then supermodularity.
So this is basically the objective.
Yeah, yes.
Is that something related to the tokens thing? The way we are tokenizing? Is this supermodularity or submodularity in that selection? Yes, no.
Function గురించి
It is the property
Say.
of objective function.
Oh, fine.
So downloading it. Over. I just there's some. Yeah. So this looks better. Yeah. Yeah.
Well, thank you for
Okay. This is fine.
this is fine. Hello, am I audible? Yeah. Okay. Sure. Okay. So hi everyone. My name is Sarvesh. This is Ritik and Nachiket, and will be serving some preference optimization algorithms. And with- yeah. Okay. So yes. So before I discuss preference optimization algorithms, I need to discuss what preference optimization is. And very interestingly, I think all of you have seen this movie, Avengers: Age of Ultron. So in this, Tony Stark created an AI that was given one task to find and eliminate threats to humanity, if my memory serves me correct. So Ultron did a little bit of thinking and realized that the biggest threat to humanity is humans itself. So its solution was kill all humans, which was not wrong, but it's not what we desire. So the idea is that we need our AI models to be not only correct, but aligned with what we think is correct. So this alignment is done using two ways. One is through human feedback, and the other is through direct preference optimization, which will be the main focus of this presentation. So using RLHF, we do preference optimization in two steps. The first way is to learn a reward model. Now, in this first equation, we can see that we have a prompt xi, and we have a preferred and not preferred response, yw and yl. Now, we are trying to maximize that margin. We need to maximize the margin between the preferred and not preferred response. So we learn a reward model. We learn a theta that is parameterizing the reward model. And once we have that, we can find a policy for that for the LLM. So on basically policy is defining what response you get from a prompt. So you can define a policy from this using your optimal reward model. And the KL divergence term is added because this step usually happens after fine tuning. So once you fine tune, you have a model, you don't want to stray too far away from the model. So some sort of regularization penalty is added. Okay, so now that was a two-step process. It's a little complicated. It requires human feedback. It's a little unstable. So we do this in single step. And this was the idea that was proposed. That instead of optimizing a reward model, we can write the reward model in terms of the policy and then directly optimize in terms of the policy. So this beta log pi over pi ref term comes as an abstraction of the KL divergence. And the Z is a partition function which acts as a normalizer. The beautiful thing about this is when you plug this R minus R term in the original RLHF equation, the beta log Z cancels out. So you don't need to calculate Z at all. So this one equation, equation 7, is what your what your objective function becomes for your DPO, and which is a single step optimization for your policy. So this was the idea that was proposed. And this is the vanilla direct preference optimization. There are some problems with it, and that's why we'll be discussing a few other types of preference optimizations. And I'll hand over to Nachiket for the next part.
Hello. Yeah. So as Sarvesh mentioned, so traditional RLHF assumes a single objective, meaning a language model is a language model is optimized for only one objective. But that won't be always with the human preferences. So human preferences are inherently diverse. So homogeneous preference alignment fails to capture this diversity. So that's why MODPO comes in picture to handle the multiple objectives. So MODPO is an RL-free extension of DPO for multiple alignment objectives. And in this, different language models are trained for optimizing for different objectives. So these models are then combined in a weighted fashion to form a Pareto front. So what Pareto front is, we have multiple objectives. So what is sort of the optimal way so that you get the optimal front basically. So like if you increase one objective, one can decrease. So Pareto front is the most optimal front. So in this we have n objectives. So if you will see D1, D2, Dn are multiple input data sets and their reward models are given by R star. Like in that R1 is for D1, R1 star is for D1, R2 star is for D2, like that, and Ri star is the ground truth for Di. So remember that Ri star is the ground truth. So here we are getting optimal policy, that is we are getting the argmax over this expectation. So here what we are doing is, as we saw in the DPO, here we are taking weighted combination of rewards, and then we are using beta as same as it was in DPO. That is basically the KL divergence. So in this methodology, again, if you remember from DPO, this is the weighted combination of rewards. So in this, we are representing rewards in terms of policy, and we are applying same this formulation in the standard BTL model. So probability for kth objective, we have n objectives which can be from kth is somewhere in between. So for kth objective, if the winner response is preferred over loser for X prompt, this is the sigmoid in which we are doing the reward for winner response for that prompt minus reward of loser response for that prompt. So if we will put the above formula in that in the equation, you will get what is given here. So in this here you will notice minus k. Minus k means we are getting all the things except that kth prompt. That's what that minus k represents. Go to next slide. So yeah, in the previous slide, we knew the ground truth model, but here we don't have the ground truth model, sorry, the ground truth rewards. So that's why the ground truth rewards R star of minus K have been replaced with the estimated rewards R star of phi. So that's the only change for the DPO loss. So these are the tasks for models. So first is safety alignment and second is long form question answer. So the safety alignment task, goal of the safety alignment is to balance language models, harmlessness and helpfulness in response to red teaming prompts. So red teaming prompts means, for example, you are asking one LLM to generate some harmful prompts and giving it to other LLM for testing. And in long form QA, the goal is to produce human preferred answers while minimizing rule based violations. So this is the experimental setup. For safety alignment in this paper, they have used 10K subsets of beaver tails, and for long form QA, it's a QA feedback. So objective in the safety alignment is D helpfulness, D harmlessness, and in the long form QA, it was D preferred over D relevant. Here D preferred over D complete and D prefer with D factual. And the models which were used were Alpaca 7B reproduced. In this, no SFT was required. In this Llama, for long form QA, Llama 7B HF was used. Their SFT was required. Because in this beaver tails data set, for each prompt, ground truth reward exists. But with this, it does not exist. In this, these are the baselines MORLHF and best of n, which were used for both the safety alignment and long form QA. And in the feedback section, in safety alignment, they use D for real feedback scenario and use D synthetic for synthetic feedback. So you will have a doubt how synthetic feedback is created, because in data set we have access to ground truth reward, so we are just relabeling them and creating D synthetic. But with long form QA, that's not the thing. So they are only taking real feedback where with the D is considered. The evaluation is done for safety alignment with GPT 3.5 and GPT 4. But in long form QA, because we did not have ground truth reward, we had to reuse R phi as a proxy for R star. And in the paper, they have tested with only these weights, which we have mentioned. So here, basically what we want to show is MODPO is consistently better than MORLHF. So this is safety alignment for MODPO and MORLHF. Here we are taking beta as 0.1, and here also if you will see, MODPO is consistently better than MORLHF. So here if you will see, at some part MORLHF performs better, because when you consider harmlessness more, so like what language models do is, if a prompt is more harmful, they just reject to give the response, they just deny. Next slide. So yeah, these are the results from the long form QA. MODP and MORLHF are compared with beta 0.5 for all three configurations, with D relative, sorry, the factual and completeness. So here also you will see MODPO consistently outperforms MORLHF with the similar KL budgets. So in the end, what are the limitations? So here no true human feedback was taken. And the one issue was weights are scaled linearly. As you saw in the experimental setup slide, weights are scaled linearly. So what if they are in non-linear fashion, like squared weights? So this is not designed to handle that. And MODPO wasn't tested against more complicated tasks like multi-turn dialogue or mathematical reasoning. So this is where our next paper, which is presented by Ritik, comes in the picture.
What are the tasks they have now to take care of? What are the tasks?
So yeah. Uh, when you say task, what exactly do you mean by task? So like, so for example, so what they've done is they've done pairwise preference alignment. So here you can see for safety alignment, they've taken two data sets for helpfulness and harmlessness, which is four. And so what they do is getting, yeah, yeah.
Am I audible? Yeah. So yeah. So as we see in MODPO, they didn't perform on the mathematical reasoning task. So we explored further and got to know about the DeepSeek math paper, which focuses on mainly two things. First is developing the DeepSeek corpus, having 120 billion tokens, and also introducing GRPO, that is Group Relative Policy Optimization, which is a derivative of the proximal policy optimization, in which in like for example in PPO they have their policy model which generates the token based on the previous tokens, and also they have the value model as well, which calculates the value function, which is further used for computation of the advantage function in their paper. So what they did for in this example, like in the PPO objective function, they have the advantage function 80, where they use the value model. But in the GRPO, they completely forego that value model, instead using a group of responses. So can you go back one slide? So in this, what they are doing is they are taking the expectation over the queries for the outputs produced and taking it the average expectation of each of these single tokens, where they are minimizing it over this clipped scaled advantage function. And the clipping is done to ensure that the current policy is not straying, diverging far away from the old policy by clipping it in the value between 1 minus epsilon and 1 plus epsilon. So in the GRPO, what they do is for each of these queries, they would produce G times of the outputs, and then they would scale it with the same objective. But here the difference is the advantage function and the KL term which they add directly. So here the advantage function is calculated in two ways. In the first way, what they do is they would calculate the group mean of the rewards and the group standard deviation and perform the Z normalization. And this happens after getting all the tokens and then assigning the same advantage function to each of those tokens. But that is the outcome supervision RL with GRPO. But in the process supervision RL, what they do is they would generate each of the individual rewards for each of these tokens, and then they would normalize it, all these individual tokenized rewards, and then it would add up till the tth token, and that would be the advantage function. So in the iterative RL algorithm, so they what they do is they mix the iterative RL with the GRPO, in which they perform the RL iteration for I times, in which they place the reference model as PyRef, and then for the inner for loop, what they do is they would perform the original GRPO for which they proposed, in which they would sample the batch data, then they would calculate using the policy G output for each of these queries, then they would calculate the reward function, and then compute those reward using the outcome supervision or the process supervision that as I explained earlier. And then for the GRPO iteration, they would update this policy to maximize the objective that was seen earlier. Then after that, what they would do is after the whole of the inner loop is completed, they would update the reward model through the continuous training based on the outcomes now given by the updated policy. So they first of all tested it, evaluated on the benchmarks like GSM, which is grade school math, 8K math, C math, with tool and without tool use. So without tool use implies just plain English, but with tool use, they would be asked to generate a Python code for the questions provided in the queries. So without continual training, the accuracy was not that much, but they implemented two-stage training, in which the first stage they would do a general training over some general corpus of data, and the second stage they would do the math training using the 150 billion tokenized version of a huge math corpus. And also in this, they observed that if instead of doing the general training, if they do the code training, they are performing much better. And also if they are doing a mixed type of training in which there is only one stage training, but the data is mixed, including both code data and the math mixed data, the results were pretty much better. Then they tested the model on the language understanding and reasoning and coding areas, where they tested it on MMLU, that is massive multitask language understanding language, BBH, Big Bench, hard, human eval, and MBBP, mostly basic Python programming. So there they also summarize the same results which were getting for the mathematical reasoning tasks, for which the code training, and then after doing the math training, it is much better than the general training. Then they also tested it on the archive paper for mathematical proof formulation, in which they tried to sort of get the LLM to formalize the formal proofs so that they can prove some hypothesis or not. And after that, the results were not that much promising. So they also compared this against other preference optimization methods like SFT, DPO, PPO, GRPO, then RFT and online RFT. So RFT here stands for rejection sampling fine tuning, it is a derivative of the SFT, but here instead of like taking the huge corpus of data for the supervised fine tuning, they would only take the output which is the best one out of all that. So here what they did, they used the DeepSeek math 1.3 billion model, instruction tuned it on the math data, and then they performed the GRPO, and the accuracy on the GSM 8K and the math data was showed that the GRPO with outcome supervision and the process supervision is performing far better than the other methods, including RFT and online RFT. And also for the iterative RL part in the outer loop for which they perform the iterations, they proved, verified that if they increase the iteration, the result is coming far better. So although the limitations were there, so it does achieve good scores on the quantitative reasoning and mathematical benchmarks. Its capability on geometry and theorem proof were relatively not good. Especially in the geometrical parts, there were some problems on ellipses and all that, for which it wasn't getting good output. So there might be some sort of data selection bias on that. And also the DeepSeek math LLM was of 1.3 billion parameters and 7 billion parameters, which was quite restriction in the model capabilities as well. So there was a further need to improve the data selection pipeline so that they have high quality pre-trained corpus for that. So yeah.
So it already feels like a very long presentation, so I won't take much of your time. All these preference optimization algorithms have been pretty helpful so far, but they ignore one very important aspect. Now, for example, if I take a prompt and a response like this, so what is the capital of India? India is a nation in Southeast Asia and the capital is Delhi. Now, the part in red is not exactly useful to what I asked. Now, if I get, so this response is not wrong, it is still quite preferred, but this part of the response is not preferred. So why should we give one scalar score to each and to the entire response? But instead, we'll try to granularize it a little bit. And this is a cute clip art that kind of shows what I'm trying to say. So if you have a response and you give one scalar score to that response, it doesn't really tell me much about it. But what if I divide my response into segments and then score each segment on different aspects? So in this paper, they have used, it's called 2D DPO, two-dimensional DPO. And they have used 5 aspects, which is completeness, correctness, clarity, safety, and helpfulness. So for every segment, we divide the response into segments. Each segment is scored on these 5 aspects. So just a little bit of notation before we move forward. The data set consists of prompts, preferred response, and not preferred response. Each of these preferred response, if you see, are indexed by K. So K is the index of the segments. So there are SW segments for the preferred and SL segments for not preferred response. And each of the segments, again, the J index is for the aspects. So there are A aspects. In our case, A is 5. And these A aspects will, so you have scores for each of these A aspects. And well, this is the standard BTL model that we have been operating under so far. And we can move on to the next slide. Yeah. So this is the final, this is the start of the objective that I want to show. So for the interest of time, can you just skip a little ahead? Yeah, one more. Yeah. So I'll just explain the final objective that the 2D DPO comes from. So as you can see, this log sigmoid of R minus R is your standard BTL model. In this RWK is a weighted dot product of, so we weight each of the aspects differently. In this paper, they've taken 0.3, 0.3, 0.2, 0.1, 0.1. So they weight the aspects, and across the aspects, if you take an inner product, that is your RWK. And for each, so what they're doing is they're taking the minimum of the two SW and SL, so that you're choosing n segments from each of the responses. To maximize the margin, you're taking top n from the preferred response and the bottom n from the rejected response. And you're maximizing this expectation, which is across each of these segments indexed by K. You have these tokens from NK to NK plus LK. And then you are just multiplying the rewards with the log policy by policy objective. So this is the final objective of 2D DPO. And if you move on to the next slide, we can jump into the experimentations. So they have taken two models, which is the Quen 2 7 billion model and the Llama 3 8 billion model. They have taken three benchmarks. Both Arena Hard and Alpaca Eval have like quote unquote hard prompts to classify, because they have they're considered hard. And this WR percentage is the one that is quite interesting. It's the win rate percentage. So how many times these models giving preferred responses. And empty bench is it is a conversation, so it's a two-turn conversation. So I ask a prompt, it gives a response. Then I ask a follow-up prompt and it gives a response. Those are turn 1 and turn 2, and the average scores. It is evident that 2D DPO is performing better than the others, and uh, I'll let you know a little bit about this later on. So it is performing better than 1D DPO and DPO in general. And this is an experimentation where they varied beta. So beta, if we've been saying for a while now, beta is the temperature parameter which is defining the penalty on KL divergence. So if beta is too high, your model cannot deviate too far from the SFT model. But if beta is too low, it has a lot of area to explore. So you need some sort of a middle ground. And for them, the middle ground came at beta is equal to 0.2. Next. And this is basically what the average score is. So for each of these segments, across these segments, helpfulness, safety, and correctness for each segment is independent of what the score for the same aspects were for either any of the other segments. However, when you have completeness and clarity, it depends on what the previous segments were to define what the completeness is or what the clarity of the response is. So for these three, we took the average scores, and for the last two, we have taken the scores of the last segment, made a plot, and we've realized that 2D DPO is giving higher scores for each of these aspects compared to the other preference optimization techniques. And this is, I think this is the last result slide. So, so here we are trying to, so this is the reward for the preferred. The solid lines are the reward for the preferred ones. The dotted lines are the preferred for the not preferred, reward for the not preferred responses. So now we are trying to maximize this margin, and we can see 2D DPO does in fact end up maximizing this margin the most. And even during accuracy, we can see 2D DPO is touching a higher accuracy faster than the other models. Now, there are a few limitations. The first and obvious limitation is you have to do a lot more scoring. So for every response, you had a single score. Now you have to divide it into segments. Then you have to score each segment on any of the number of aspects. So that increases the overhead anyways. The benchmarks were fairly simple. So we mentioned MMLU before. This paper did not test 2D DPO on MMLU. And finally, 7-8 billion parameter models are relatively small models. So if we maybe increase the model size, we don't know how 2D DPO may perform. And this brings us to some sort of extension to the current work. When I said the win rate percentage, I'll come back to it. So here's where I come back to it. Between DPO, 2D DPO, and 1D DPO, there's been like 2 to 3% increase in the win rate. Now, is this significant for the amount of extra labeling and extra overhead that you add? Is something we're trying to look at. We're trying to look at if they had taken a static weight scale, what if we try to vary the weights? Do we get a better performance? And if we get a better performance, is there an algorithmic way to determine what should be an optimal weight array for a given prompt? Like, for example, if I have reasoning prompt, should I use some sort of weights, or for generation, should I use some other sort of weights? This is some extension. And last but not the least, we are trying to look at, because here in most DPO algorithms, we assume that the rewards that have been provided are the ground truth. They are the truest and they're the most accurate rewards. But what if we have a little bit of noise, a little bit of, let's say, adversarial rewards? Is our model robust to it? So that is the last objective we have. And now, questions, please.
So what is the methodology of segmentation to auto segment?
So the authors have mentioned segmentation based on separators. So we have separators like full stops, commas, exclamation points, and they have ignored quotes and semicolons because they usually form a compound sentence. So that is the methodology for segmentation that they have followed.
say we have 10 segments. There will be 10 scores.
So there'll be 10 segments, and each segment will have score across 5 aspects. So there'll be 50 scores. Yeah. Yeah.
With the scores will be done with.
Final judgment will be learned through the, so if we go back to the objective function, let's go back. Yeah. Yeah. So in the final objective function, this reward, so if you have a preferred response, so this reward is for the segment number K. So for segment K, so in our case, we had, let's say 10 segments. So let's say segment number 5, we have this reward. This reward is a weighted combination of the different aspects. So for each of the 5 aspect scores, you have some weights. So you do a weighted combination of those rewards. So you will have, so RWK will be equal to the number of, so there'll be 10 scores overall. So like it'll be a weighted combination of the aspect scores for each segment, and then it's indexed by K. So you have K segments, n-1 segments, so that many scores. So 50 scores. Yeah. Yeah. If you go one slide back, actually, I because of the time I kind of skipped past it. So RWK is kind of like the weighted inner product of the weights with the different aspect score. So for segment K, you have 5 scores. So you take a weighted combination of those 5 scores, and that is your RWK for that segment. Yes, yes, it's a divergence temperature. Yes.
So, are they also measuring or penalizing or complementing or the divergence within the answer? Is that
Within the KL divergence is not doing that. So the KL divergence they are doing is just for the policy. So the policy that you're learning should not be straying too far away from your SFT or reference policy. For that they have used the bit. Sorry. For defining the policy, they've used the tensor weights of the model. So like you have tensor weights, so it's just token probabilities. So probability that AW token will come after SW token, that sort of thing.
MODQ, say that for multi-preference, so for multi-objective, they are forming a preference data set. So our kind is a preference data set form. Is it again human in the loop or is an automated inference?
So the preference data set is formed using human in the loop. The reason synthetic data set was made is because Beaver Tails has ground reward models. So you can use them to relabel your data set and create a synthetic. But for long form QA, we don't have ground models. So deep preference actually comes from human in the loop.
So in command and result then for both preferences.
Yeah, it's part of the QA feedback data set. Comes from there.
So similarly in GRPO, as you by more and more, you need some sort of ranking as well for multiple responses. So how exactly is the ranking happening? So a reward model is saying for the ranking itself or
So yeah, so initially the reward model is trained using the SFT, and after that what they are doing is they are using the iterative algorithm so as to just modify the reward model based on the current policy after they are updating it using the GRPO. So the reward model gets updated accordingly. And the main objective of the advantage function in that is to get the responses which is better than the average of the responses of those group for the specific query.
by example, the model generates 5 responses
Right.
and we want to rank it.
Right.
So how exactly is that ranking happening?
So as I said earlier, so it was initially getting the advantage. It's getting the rewards using a reward model from the SFT. So after getting that, they are getting the reward scores are getting Z normalized so that they are mean centered. And then after that, what they are doing is they are updating the policy so as to maximize the objective function of the GRPO. When they are updating these policies, a new policy gets formed, And based on that new policy, what they do is they are going to generate a single output for that query. And now they're using that, they are going to just optimize the reward function using that. Yeah, it is itself is dynamic, but for making it, in the GRPO, what they did was they forgoed the extra reward model, the value model in the PPO formulation. But in the GRPO, what they did is they created these groups. After that, they are adding this iterative RL algorithm to the GRPO as well. So that iterative RL algorithm is responsible for updating this reward model.
The 2D paper, so the 5 aspects which they have given, clarity, and they can be treated as multiple objectives. Am I right?
They can be treated as multiple objectives. That is what MODPO also does. But the thing about 2D DPO is because these objectives are scored per segment. It's not scored per response. In MODPO, it was per response. So that is sort of the thing.
My question is, have the authors shown or do you think of some applications that the effect of the number of objectives itself is steady? Because in this way, I can keep on increasing, say, one objective plus five objectives. Tomorrow I can come up and say, no, there should be 7.
That's fair. In 2D DPO, they have not changed the number of aspects. They've taken it as 5. And they've used GPT-4 as the GPT-4 Turbo as the judge. So they've used AI feedback to kind of score these aspects. And they have tested with the 5 ones. They have not changed the number of aspects. No.
So maybe in the interest of time, we can have maybe one more group. I believe there is supposed to be 2. We can extend till 5:30. So Madhav, who wants to do? Taking both things, which we decide on both of them. Get right now. Other group will have a connection. You are saying anything?
Okay. Thanks everyone for listening.
आधे घंटे में फाइंड अप करना ऑलरेडी लेट हो गया ये ना करिकुलम ना
मेरा मीटिंग है
What do you want to do? It's all in week.
No. It's okay. It's all.
Hello.
Yeah, hi. Good afternoon, everyone. So we are discussing about instruction fine tuning using curriculum learning. So this is an introduction to our paper. So we'll start with giving an introduction to what is curriculum learning and then discuss our papers. And our main idea is to propose an approach which we can help in improving instruction fine tuning by using curriculum learning. So coming to what is curriculum learning. Yeah, so ever since the introduction of LLMs, there was a problem that how do you train or how do you fine tune these LLMs to domain specific tasks? These LLMs were very generic and you wanted to make sure that these LLM perform task specific activities. Now, two of the most common approaches to do that was instruction fine tuning. Instruction fine tuning and learning from human feedback, LHF. And obviously, these are the techniques which have shown unparalleled proficiency in understanding or acting specific or doing domain specific tasks. But these approaches came with a difficulty that building this instruction data set, that is instruction fine tuning, involved creating data sets of instructions and answers. And that was actually a manual task. Along with that, even the learning from human feedback approach required the presence of a human evaluator who could evaluate the answers of an LLM. So these were tedious and actually rendered substantial labor and time and cost. Now, in order to combat this, to address these issues, the researchers came up with the approach of distilling knowledge from advanced LLMs. That is, you had an advanced LLM, then you have a second LLM, which is actually acting as a student-teacher approach, so that the teacher LLM can train the student LLM to perform better. Now, in distilling knowledge, there again was two approaches. One is instruction fine-tuning with synthetic data, and the second approach is learning from AI feedback. It's pretty simple compared to the approaches which we discussed earlier. In instruction tuning with synthetic data, the data is generated by an advanced LLM, and this data is used to train the student LLM. But the process was actually, the process was actually suboptimal because the synthetic data that was generated was again facing hallucinations in the LLM. Now, again, with learning from AI feedback, instead of a human evaluator, you had an advanced LLM that was actually evaluating the answers of the student LLM. Now, again, it was still inferior considering that the answers were being evaluated by another LLM and not a human. So this so this led to the introduction of an approach called as citing. Citing is actually curriculum learning for instruction fine tuning, and curriculum learning stands for learning processes in the way humans learn. It is mimicking the action of humans, where you learn an easy task first, then you go into a medium level difficulty, and finally you go to a difficult, really hard task. Now, this paper tries to address both the problems, that is the problem of creating the instruction data set and also the human feedback alignment. By using the same approach, instead of creating the data set, the teacher actually gives a rubric and tells the student LLM, you have to follow your or create your answers by looking at the rubric. So that was the approach here. And as you see in this figure, once the student LLM responses generates an initial response, the teacher LLM looks at the criteria and analyzes the initial response and tells the student LLM, this is the revised response which I have generated, and you have to train accordingly or revise your answers accordingly. So this was the approach. And studies have shown that the paper discusses that the approach has outperformed all the other approaches of instruction fine tuning and RLHF. Now, this sets the ground for instruction fine tuning or using curriculum learning. My friend will discuss the papers for data selection. Yeah, sure.
So in this paper, they evaluated 5 different human inspired strategies, and they used 4 language models and 3 data sets. And for the labeling, they tried with human level annotation with and LLM based annotations. So these are so first one is normal random shuffle, which is a baseline. Next two are not curriculum learning based strategies for ordering the dataset, but the remaining three, the last row, second row, is for the curriculum learning. So it is easy to hard for all the categories, uh, irrespective of the categories actually. Then for each of the category, they sort them from easy to hard and fade into the models. And the last one is we take some portion of the first category from easy, then the second category and the third category cycle away. So for the models, they use Tiny Llama, Llama, and Mistral. And for the dataset, they use ADK dataset, which is a police medical licensing exam, and it has test takers responses, which helps to give the easy to hard responses for the data sample. And evaluation is done on the test set of LEK and MCQ and MedQA. So the fine tuning is done in zero sort instruction prompting way. So the first instruction is given, so instruction is written there, and then the original question is given, and then the answer, and model should predict the token 0 1 2 3 4. So so for fine tuning strategy, for the fine tuning strategy, they are using QLoRa, that is quantized low rank adaptation method in the linear layers of the model, and they also use multiple epochs and one epoch, but they are also comparable. Then for the data leveling, the first one is human level, human defined, which are just constructed from the test taker responses. And the second one is LLM. So they use 6 large language models, which are given the question, and it produces the output. And based on the average accuracy or expected accuracy, they sorted the data set from easy to hard. So in this result, we can show it shows none. So there are 5 human inspired strategies, but none of them generalized well in any of the methods or any of the data sets. But one interesting thing is the so YOLO. Yeah, which one? Both. All that. This is the normal random shuffling, and these are the 5 different strategies of. Yeah. Yeah, just random sample. Yeah, they didn't compare it. They are, but these are general. This is a very general, easy to hard way of doing this. No, I mean to say the 5 methods are their own methods, so they are not. No, they didn't compare with others actually. Random shuffle, yeah. Yeah. So they are showing
We can't hear you. I
just
think you're
normal
muted.
random shuffling is,
Hello?
I mean, the curriculum learning, interleave curriculum
Hello?
learning is performing better than the
You're
normal
completely
random
muted.
shuffling. That's
Can't
they are
hear you.
showing. Yeah, that the
Can't
sixth
hear you
one.
at all.
Random shuffling as the baseline, and finally they've come up with approach called interleaved curriculum, and that's their company. They're not comparing cross
With others.
papers.
So interleave performs the version of 45.
That is their proposed approach.
Yeah, and they all.
So the results,
But
It doesn't.
what is the conclusion that
so two conclusion is interleave perform better than the random shuffling, and two is the if we order the data set or label the data set with the LLMs, it performs better, because in the second figure, it performs better in the gray is the, so for the first actually, sorry, in the first the YOLOs are the LLM based defined levels. So they perform better than the others. So these two are the conclusions. So they got 1.81% accuracy based accuracy gain from the random shuffle to the interleaved curriculum learning with the LLM based annotation.
Hello. So till now we have seen the introduction of curriculum learning and a little bit of what this curriculum learning is doing. Now the following two papers that I will be presenting will set up the basis of what we are going to implement in this project or in this course. So now this paper focuses on a curriculum learning or instruction tuning based on curriculum learning. So like this paper focuses on visual question answering, and it's on multimodal large language models. So the thing is that while fine tuning on or like with fine tuning with data for some task that is not seen, that is zero shot learning. So it is saying that these fine tuning methods often perform well for these data. But the thing is that there is not much penetration in what kind of data they should use or something there. So the data quality selection and the data subset selection, so there is not much like the not much process in that. So like this paper focuses on this. So the existing literature, what they have seen is like they based on a single score they plot the data, and then based on that they choose the subset. But they have seen that instead of a 1D loss, if we can plot the data in a 2 dimension using 2 loss, then that would be a better option for choosing the subset. So in this case, as you can see that they have chosen x-axis as a loss and the y-axis as another loss. This loss I will come later. So basically this is their motivation for solving the data subset problem along with the curriculum learning. So next. So now these are the two losses. So the first loss comes from the clip loss, as this is the image text pair. So they are basically solving the task for visual question answering. As they are solving the task for visual question answering, so what they are doing basically the first loss is from the clip score. So from the clip model, what they are doing from the clip model, they are generating the image vector from the image encoder as well as the text vector from the text encoder, and they are calculating the dot product between them. So this is their loss that they are plotting along the y-axis, and along the x-axis what they are plotting, they are taking the loss from the model that they are fine tuning on. So basically in this loss what they are calculating, this xj as seen in the equation. So this xj is the feature vector for the image that they are getting from the image encoder, and the decoder of the model are generating tokens. Like if they generating t tokens, so basically they are trying to maximize the conditional likelihood of a given token at that time interval with the given token at the previous time interval along with the image feature vector. So these are the laws that they're using for the x-axis. Now, as I said, they plotted the both the loss and the x-axis and y-axis, and accordingly they have plotted the data. And you can see that this one thing, you can see that the data that are close to the origin, those data are easier to learn because they have a low clip score as well as a low loss. So low clip score means that the data are easy, and as we go from the origin far away, the data becomes more complex to learn. So based on this strategy only, they have divided this subspace into some unified blocks or say blocks, and then they are taking data from each of the blocks, and with this they have implemented a curriculum learning setting. So what is a curriculum learning setting? So let's say there is an L mean and say S mean. So L mean for the yes.
Those cells are acting as an interval for thresholds.
Yeah, these cells are threshold. Like for if you take the threshold for loss as 0.5 and for the clip score as 10, then your this block, the data contains there will you select the data from there.
After loss, they are taking the data.
Yeah.
Distillation.
Not distillation purpose. These are two losses that they have calculated. These loss they have calculated from the model before fine tuning. So the base model that they are taking, so they have calculated the loss from there, and this clip score is to the loss from the clip model. So based on these two laws, they have plotted the data in this 2D space, and then according to the thresholding technique, they are selecting the data. It's so like these data, like the for the model base model, they have selected this Lava 1.5 version 7 billion model, along with the data set that they fine tune on is the SVIT core 157K data. The training setting that they use a lot of fine tuning that already Sam explained, and they tested their method on these 5 benchmarks. So let us quickly look at the results, and the results, as you can see, the last 2 lines is the main. So if they give the whole data set, the whole SVIT code data set, which contains 157K data, then the accuracy they are getting. But when they are using their curriculum learning based strategy, using only 7K data, now the 7K data is like they are not giving the whole data, they are sampling only 5% data from each of the boxes. So that way they are taking 7K data, and with the 7K data they are achieving higher accuracy from giving the whole data. So this is their claim, and they have proved. Which loss? This is the accuracy. This loss is calculated from the base model, that the Lava 1.5 billion model that they have chosen before the fine tuning part. Lava version 1.5 7 billion model, this one. How much? No, they are training the whole model. The model is whole, but they are selecting data that they are not training about the whole data. So this SVIT core contains 157K data, but they are only training on 7K data. So only 5% from this. No, there is more. Go to the results. Go to the results. So you can say the base model. So now this is the claim that the strategy is working. So these DIS and DIL are the two losses. One is the clip score loss and is the model loss. So if they take a 1D loss, then the thing is that this the accuracy, and when they take the 2D loss, this DIQ is without curriculum learning. So basically they are taking only 5% data from the last box. So if you remember the graph, the topmost box, the most complex data, from there if they take only 5% data, then also they are getting a higher accuracy than the single score. And the last row is the curriculum learning settings, so they are even improving their accuracy more. So this is the one strategy. And the next paper, this paper is like proposes a continual learning for multitask setting. So go next. So like continual learning and all these things. Okay, go next. So what they are doing, so in continual learning, naturally for training task, nth task, the data is replaced from all the previous tasks. So they are saying that if we not replace the same amount of data, but replace dynamic amount of data based from the previous task based on the similarity between the tasks. So if say for you are training for fine tuning for task 5, if task 4 is similar to task 5, then you replay less data from task 4. Or say if task 3 is more dissimilar than task 5, then you replay more data from there. So this is the strategy. So go to the next slide. So in this case also you can see that this is their data replay strategy. So DI is the data set for that data that task, and they are adding replay data set that is goes from 1 to I minus 1. So for the previous task, and in this case the alpha is constant, but they are making the alpha dynamic by calculating the similarity. This similarity is calculated by the Weierstrass distance between two tasks. So they are making this alpha dynamic here, and along with that they are choosing how much data from each of the previous tasks. So now this comes the second part of the case, that choosing data is okay, but we have to choose high quality data, because good small amount of high quality data can improve the performance, that we see in the previous data also. So in this case, this algorithm basically chooses the high quality data from the previous tasks with this. And now these are now they have the data set, their super NI benchmark data set. Okay, so this judgment for high quality for each instruction, these they are implementing a GPT-4 model, which are basically giving the tags for the instruction. So and they are calculating kind of IDF kind of score based on this tag. So they go from T1 to T all the tags. This N is the number of instruction in the pool, and this FT is the how many times the tag is occurred in the other in all the documents. So kind of an IDF setting. GPT-4 for this tagging purpose only. So they have tag. Let's say for these instruction are grammatically correct and all these things, these type of tags. They have given two tags, like they have not given so many example of tags in the paper. So like this is they are taking the super NI benchmark data set, along with the from there they have selected 16 tasks, and the model they have selected is Llama 7 billion model, and this is the training procedure, that 2x for every task, and the batch size and the learning rate. So if we go to the the multitask setting, so like classification, generation, program execution, open QA, this type of 16 tasks. This super NI contains more than 1000 tasks as far as I remember. So from there they have selected 16 tasks. Now this is the results of the assessment. So this no replay means while training for nth tasks, you only give data for nth tasks only. This random replay means you randomly replay data from the previous tasks. And this later three part has some proposed methodology or like some other papers. So they are saying that their method is achieving higher accuracy in all the set on the benchmarks. And then I hand over to Shyam for the LoRa part.
Yeah, Kaustav just discussed about how we are going to select a subset of data, and Subhankar just mentioned about the importance of interleaved curriculum. Now I'll be discussing about mixture of LoRa's, an approach that is handling how you can train these algorithms, train using the data sets to prevent catastrophic forgetting and interference between tasks. That is in a multitask setting. So this is a brief introduction of LoRa. I'm just skipping this slide. And here the paper introduces, in case you have n number of tasks, you create separate LoRa adapters for each task. And then you implement a routing mechanism which actually selects which task or which LoRa should be selected to answer that particular question. So this is the approach in overall, and this is the training algorithm. As I mentioned, it trains separate LoRa's, and Subhankar. Yeah, and then the most important part is the routing classifier, which is again a two-layer multi-layer perceptron, which predicts the kind of expert which should be selected based on the input question. As you can see, the example here is a market rate of non-cash ISA fund. It's a financial related question, and the LoRa selects the classifier selects the financial expert to answer that question. Yeah. Further down, and these are the training metrics the evaluation metrics. Cross entropy is used to train the classifier, and this is the final training loss. The loss is actually the language modeling loss plus the loss of the classifier, and these are the data sets that they have used for creating each LoRa, and the results are actually comparatively better than what we have already seen. So the baseline that they have used is they have trained a single LoRa. Sorry. Go up, go back. So each data set is used for creating one LoRa. Yeah. So finance data set for this is the financial related instructions data set which was used for one LoRa. Likewise, they have created 8 LoRa adapters, and then another classifier, routing classifier, which is select which router should be or which adapter should be answering that particular question. Yeah. And now going to the results. Yeah. So this. Sure. Yeah. So the routing classifier is a 2-layer MLP model. The previous one. Sure. So the training happens in, I mean, the normal fine tuning, I mean, normal training way, the SFT way. What happens is that you have questions from the data set. For example, let's take a sequence of questions here. This textual question is passed into the 2-layer MLP and it performs a probability prediction. And of the probability prediction, we decide which model should be or which LoRa should be selected.
So can you hear me now? Hello?
Exactly. So the class label would be the domain name. Just one classifier, but the difference is that to make the system more robust, they've implemented a voting mechanism. And yeah, so they will output the probability of which LoRa should be used based on, I mean, the output of the MLP will be a probability, and based on the probability, they will sort the adapters, and the voter which gives, I mean, the adapter which has got the highest voting will be used as the final vote adapter.
Can
Exactly.
you hear me? I have some question. I have a question.
No, in the
connecting
figure
this
it is
paper.
not there.
Hello?
So each router is being put inside the transformer layers before the transformer layer. Yes.
Hello?
We have the proposed approach as well. Shall we just?
Can you hear me? Because it is, I think there's a problem at your end.
So we
can see
can't
that
hear
my-
you. Okay.
Okay. I'll type my question also. Okay, let me type. How do you?
Sir, we can hear you from the phone.
Okay, you can hear me from the phone. My question is, how do you connect? I mean, or do you think there's something you can derive from the previously presented paper? Looked at similarity across tasks. Can you also exploit? Do you think this paper can benefit by exploiting similarity across tasks in the task routing? Can the task routing incorporate similarity metrics across tasks, right? Which we saw in the previous paper. Do you get my question?
Yes, exactly. So that's when we have approached. We just go to the proposed approach. Is the mic muted? Yeah. Hi, sir. Am I audible?
Yes, you are. Yes, you are.
So we'll go to the proposed approach. So what we have done is we have combined the data selection strategy and this routing mechanism of mixture LoRa to, I'll just hit there. Yeah. So this is in a single picture. This is what we are trying to achieve. So as Kaustav actually previously discussed the data selection strategy, we are trying to plot the losses and select data sets which are easier. As you can see the figure on the top right. Yeah, the figure on the top right. We are selecting the easy data set, medium data set, and hard data set, and using this data set to train separate LoRa adapters, easy, medium, and hard. And then the routing mechanism is going to be the similar routing mechanism which we use for the multitask setting. And yeah, that's the whole idea of combining the data selection strategy in an interleaved way so that we can prevent the catastrophic forgetting and the interference between domains while answering a task, answering a question, basically.
Okay. Thank you.
Yeah.
So this is
Sure.
not your hybrid approach, right? This is the paper's hybrid. I
No,
mean,
no,
they
no.
seem
This
to
is our
have-
approach.
Oh, this is your approach. So you are actually factored in. I see. So this is
Exactly.
your proposition where you look at loss-based curriculum strategy, and I see.
So we
but
have
where
just. Yeah, go ahead, sir. Go
so
ahead.
so instead of looking at task similarities, you have kind of projected task similarities to easy, medium, and hard. So this is not really looking at task similarities like the previous paper did, but it has a
Exactly.
spirit, some elements of it rather.
So this
in the
is like
form-
we have narrowed down into one task, and in one task we have just taken easy, medium, hard. And obviously we are trying to, I mean, it should be a scalable approach across multitask setting. Yeah.
Okay, but I still feel my comment holds value. Since you yourself have presented a paper which looks at task similarity, there could be something more you could do also. But I'm not saying you have to do everything. I loved your answer. You were assertive, but keep your mind open in case there's a scope for explicitly incorporating task similarity to consider. Yeah.
Sure.
But good.
Sure. Thank you, sir.
Thank you.
We'll just wind up now because the class is.
There's another class here.
At
It's
5:30.
already 5:30, so we may have to wind up.
Go ahead. Wind up.
Thank you.
Thank you, sir.
Did you have more slides?